Now let us look ahead the design of IIR filter. Design of IIR filter using bilinear transformation. Okay, now like that of our previous video of impulse invariance method, here our task is also to convert any given analog transfer function to the digital transfer function. That is, we are to convert the HA of S, that is in the Laplace domain, to H of Z in the Z domain by the virtue of Z transform. So now if we consider an analog filter with the transfer function of HA of S having pole at S equal to A. So let me write it down. If we consider an analog filter with transfer function HA of S, which is having only a single pole, at S equals minus A. Then accordingly HA of S mathematically can be written as B over S plus A. So now this analog filter will characterize a differential equation which will look like be x of t. Now how this expression come? Let us look at that. So we can write HA of S to be equal to y of S over x of S, where y of S being the system output and x of S is our input provided. So this will be equal to B over S plus A. Fair enough. Now we cross multiply these two expressions and we get Bx of S is equal to Ys times S A y of S. Now by the application of inverse Laplace transform, we can write Bx of S as Bx of t. Y of S will become y of t, and in the Laplace domain the S operator multiplication in the time domain becomes a differential operator. This is the property of differentiation of the Laplace transform. And finally we get Ay of S, A will remain as it is, y of S inverse Laplace will become y of t. So by this way we can derive our expression that is shown over here. Now once again y of t can be written as y of t equals to y of t minus y of t naught plus y of t naught. Two arbitrary terms, one having a negative coefficient, one having a positive coefficient, will eventually cancel each other out, and we will be left with y of t. So that is mathematically logical to write. Furthermore, we can write y of t as d dt of y of t and integration 0 to t. Now this integral will have a integration constant, and so y of t naught will be absorbed in it. So we are left with, okay, if that's the case, now this can be otherwise written as t naught to t d dt of y, we write it as y prime tau, where prime indicates the first derivative and double prime will indicate the second and consequently third, fourth, fifth. And this is quite obvious from our partial and ordinary differential equation courses. And the integral operator will be d tau plus y of t naught. So if that's the case, we can write y of t is equal to t naught to t y prime, which is a function of tau, d tau y of t naught. Let us give this equation A. It is clear up until now. Let's move along. So now what we are going to do is approximate the integral using the trapezoidal area. What does that eventually mean? So if this is our y-axis, this is our x-axis, this is 0, this is the temporal dimension t, this becomes y prime of t, and y prime of t is plotted something like this. Say this is an arbitrary value. Let us take two projections of this two point. Here this is t naught, which is equal to nt minus t, and here the value is t, which is equal to nt. Just sampling the values on the way. So t naught, our lower limit, projected over here, and t, our upper limit, which is projected over here. So at this point, the value of the function will be y prime of nt minus t, and at this point the value will be y prime of nt. And if we are able to determine the area of the trapezoid, the approximate area of this trapezoid under the curve, that will result in our resultant integral equation. So before going into the area of trapezoid, determining the area, so this value will be equal to t from this point to this point, the length over here, because nt minus t minus n of t will give us the value t. So this is the length. Now let us recollect the area of a trapezium. Say our trapezium looks something like this. It has got two parallel sides. This one is A, this one is B, and the distance between the two sides is h. So from our primary concepts of area, we can write the area of the trapezium to be the average length of the two parallel sides multiplied by the distance between the two sides. So the distance A by B, this distance A and B, we take its arithmetic average, so it will be A plus B divided by, since there are two quantities, so 2 times the difference between the height h. So this is our area of the trapezium, and from this very concept we can write the area under the curve. So AUC, area under the curve, will be y prime of nt minus y prime of nt minus t, plus, divided by 2. So this is these two parallel sides length, and divided by 2 to bring out the average, times the distance between the two parallel sides, that is t. So we are able to quantify the area under the curve. Now let us plug in this value into the given equation A, for which we will get y of nt will be equal to t over 2 y prime nt y prime nt minus t plus y of t minus t. So t in our case is equal to nt. T naught we have considered it to be nt minus t, hence t over here is changed, and t naught over here is changed by the respective value, t over 2 over here, and this expression remains as it is. I'm sorry, there will be a closing second bracket over here. So let us mark this as equation 1. Now moving along, our initial differential equation, which was d dt of y of t plus ay of t is equal to bx of t, can be otherwise written as y prime of t, which is nothing but the first derivative of y of t, as shown over here, is equal to minus a y of t, so subtracting a y of t from both sides of the equations, plus b x of t. So what we are going to do is sample this equation, and sampling in our case means replace t with nt. So the expression becomes y prime and t is equal to minus a y and t plus bx and t. So next what we are going to do is replace y of nt with y of n and x of nt with x of n in equation 1. So in our case, equation 1 was this expression over here. So y of nt will become y of n, t over 2 will remain as it is, and y prime of nt, that is shown over here, can be taken from this expression. So y over nt will become minus a y of n plus b x of n. Remember, we are replacing nt with n, and that's why nt is changed to n. So this is our y prime and t, and consequently our y prime nt minus t will become minus a y of n. Since we are replacing nt with n, so n of t minus t will become n minus 1. So this is shifting in the time domain, that is shown over here, and the rest of the expression be y of n minus 1, sorry, this is x of n minus 1, plus a final expression y of nt minus t will become y of n minus 1. So what we have done is just plug in the values in this expression and replace its variables devoid of t. So now we are going to further simplify this. So by simplification, what we are going to do is at over 2 y of n, taking all the y of n terms out, minus 1 minus at over 2 y of n minus 1 is equal to bt over 2 x of n plus x of n minus 1. Let us give this equation 2. Just simply factoring out the coefficients. So this can be approximated as a differential equation. So 2 is an approximated not differential equation, difference equation. And we may apply Z transform to it now. So this will become 1 plus a t over 2. Y of n will have a Z transform of y of z plus a t over 2. Y of n minus 1 will have a Z transform of Z inverse y of z Consequently, bt over 2, this will be x of z, and x of n minus 1 will have a z transform of z inverse x of z. So now, from here, we are going to find out h of z. And for that reason, we need y of z to be factored out. This becomes 1 plus at over 2 minus 1 minus at over 2 times z inverse, which is equal to bt over 2 1 plus z inverse times x of z. From here we can write h of z, which equals to y of z over x of z is equal to bt over 2 plus z inverse divided by at over 2 minus z inverse at over 2. So h of z is equal to b over 2 by t 1 minus z inverse plus z inverse plus a. This is achieved by simply multiplying the numerator and denominator with the term 2t multiply t 1 plus z inverse. So now compare this expression with our given expression h of s, which was b of s plus a, and from here we can write s is equal to 2 over t 1 minus z inverse plus z inverse, which is our required bilinear transform. Let us look at an example.